Hi everyone, in this video we are going to be deriving the derivative of e to the x. For some function y equals e to the x, we want to know the derivative of it. So how does y respond when we change x? So if this is our initial y value. And so let's say y sub f is the final y value we're going to get to. We're going to get to a value of x plus some delta x. Okay, so then the change in y would be final minus initial. We have our delta y is going to be y final minus y initial. And we know that that equals e to the x plus delta x minus e to the x. Well, that doesn't help us too much. How can we simplify it? So a few things we can do. We can rewrite that expression as delta y equals e to the x times e to the delta x minus e to the x. So, if we remember the series expansion for x, we can expand e to the delta x because we're looking for some small change in x. So we can expand that part of it. So we can factor out the e to the x. It's going to equal e to the x times e to the delta x minus 1. So let's expand e to the delta x. So when we know that the series expansion for the e to the x is 1 plus x squared over 2 plus x cubed over 3 factorial and so on. But when delta x is really small, that x squared term is going to be practically 0. So all that we need for a good approximation of e to the delta x is just 1 plus delta x. So we have e to the x times the quantity 1 plus delta x minus that 1. So here we have delta y equals e to the x. Got ahead of myself for a second. E to the x delta x. And if we let that delta x get really small, infinitesimally small, we would get back an infinitesimally small change in y. So, with this, we're going to change our delta notation to derivative notation, to Leibniz notation. dy equals e to the x dx. Or the slope at some point on the graph of e to the x is always just e to whatever that x value is. There, in fact, is the derivative of e to the x.